Hello friends, we start with our next topic of networks, that is known as operational amplifier. We will see what is operational amplifier and what are the different type of numerical problems used to come under this topic in network analysis. So this is also one of the good topic in which we will see how OPAMP is linked with networks and how the problems in network analysis used to come on the basis of operational amplifier. You may go through this operational amplifier in your analog devices also. That is also one of the subject of electronics. So you will go through the more detail of operational amplifier in that subject, but here we will focus on the aspects of operational amplifier in terms of network analysis. So we will start with our this topic known as operational amplifier, and we'll see the different type of problems techniques, how to solve voltage current across loads when operational amplifier is connected in the circuit. Okay, so before going for this topic, if you have still not subscribed, like and comment my channel, please do it. Please subscribe it, because once you subscribe, it will be more easy for you to go through my all videos in a sequential manner. The description, my all previous videos is already mentioned in my description box. You can go through it and try to understand all the previous topics. So we start with our topic known as operational amplifier. So now the question comes to your mind, what is operational amplifier? In short, we call it as OPAMP. In short, we call it as OPAMP. So here are the two words. One is coming as operational and another word is coming as amplifier. So we will see both the words and the definition of both the words, that is what is operational in meaning and what is amplifier in meaning, and why it is called as operational amplifier. So first of all, we'll talk about amplifier. What is amplifier? A basic definition which all know, that any signal which is applied at input terminal of some object and finally will get an enhanced output. Okay, so if I say this is a certain device or a unit at which some input is applied and finally will got an output. Now if you applied an input say X, you will got an output say Y, and this Y is basically K times of this X. This Y is basically K times of X. Or you can say, if this is a signal is applied at the input of this terminal and somehow you will get an enhanced signal at the output of this terminal say Y. So you can say that this signal which is of some magnitude which is small in nature, now it is get enhanced by some value, and what is that value? That value is known as K. So this unit is basically known as amplifiers. What is this? This is known as amplifiers. So the very basic definition of amplifier is when any input signal is applied at the input of an amplifier, you will get an enhanced output. Okay, you will get an enhanced signal at the output of that unit. So that is known as amplifier. Okay, so there are a lot of amplifiers you will study in your EDC and ADC in your two different subjects of electronics. However, we will talk about the concept of amplifier and how it is applicable in networks. Okay, so now come to the word known as operational. Now amplifier we understand, but what about the operational? The meaning of operational means there are different type of functions which can be performed with the help of OPAMP. Okay, and that's why OPAMP is known as operational amplifier, and it is also known as amplifier having capability of mathematical operations. Okay, so operations, definitely it's a kind of mathematical operation, yes, there are operations like what is mathematical operation? Mathematical operation means simple. If you have to sum, you have to subtract, you have to say multiply, and so on. Okay, and so on. So these are basically known as operations, or you can say mathematical operations. So in electronics, you will find a category of amplifier which is able to perform different type of mathematical operations, and these mathematical operations are very useful while solving a network in different situations. Okay, so basically the meaning of operational means the amplifier is capable of doing different type of mathematical operation in a network depending upon the requirement. Okay, depending upon the requirement in the network to get a enhanced output, or an output which either a summed output or a subtracted output or a multiplied output, or you can say an integrated output or a differentiated output. So depending upon the condition of the network, an amplifier can perform a different operation, and that's why it is known as operational amplifier. And it is also known, it means you can say that OPAMP is capable of doing mathematical operations. Okay, so a very important thing which we have covered here is first, that is OPAMP is capable of doing mathematical operations. OPAMP configuration is in this form. This is a very simple diagram of operational amplifier. Now here you see these are the two voltage V1 and V2, and here are the two current I1 and I2. Here you will find two terminals, one is negative terminal, another one is positive, and finally you will get an output, say some current is flowing at the output, say I0. Okay, so this is a basic diagram of OPAMP. This negative terminal is known as inverting. Okay, this terminal is known as inverting terminal, and this positive terminal is known as non-inverting terminal. Non-inverting terminal. Okay, so this is a basic diagram of OPAMP. Say this is first. If I draw the second diagram, few changes I am going to bring here, like I am adding two power supplies here. Say this is plus V, say this is minus V, say this is V0 again. Now see, here the current is I1, I2. If for the timing I say some current is flowing is I plus and I minus, so here I have taken two more terminal and I have applied some voltage V and minus V. We will see what is these voltage, but this is another way in which we are powering the OPAMP, the applying external voltage. This is known as applying the external voltage to the OPAMP, or you can say this is basically you are powering the OPAMP. Powering the OPAMP means you are applying an external voltage to the OPAMP in terms of plus V and minus V. This value may be different. Okay, this may be, you can say it is V1, or this is V2 also. Similarly, the current is I1 and I2 also. Okay, so from here, if you see the current I0 in this, as per this diagram, is basically what? You can say it is I1 plus of I2 plus of I1 plus. Okay, for here I write it as I1, since I1 and I2 is mentioned here, I say it is IA and IB. Okay, why? Because I1 and I2 is already mentioned here. I taken it as IA and IB. So this is IA plus of IB, which is negative. So should I write this Kcl equation for this OPAMP? Yes, the value of I0 is what? It is I1 plus I2 plus IA plus and IB minus. Okay, So whatever the current coming at this node is equal to the current going out from this node. So this is I naught. So as I said, the meaning of applying voltage V1 and V2, or it is same voltage or it is different voltage, simply the meaning is you are powering the op-amp. You are powering the op-amp. It means you are giving some external voltage to the op-amp. So this is your one basic diagram of op-amp, and this is the another diagram in which we have seen the powering of op-amp. See, op-amp is in the form of DIP. We call it as dual inline package. It's an IC where there are different pins. Around 8 number of pins are there in op-amp. 8 number of pins. So there is a DIP package, and you will find in op-amp there are 8 number of pin which is shown on the op-amp. So yes, that is that you can see in your different in your ADC subject. There is no issue. But for the timing in networks, we will not go into the details of the pin diagram. Here these two diagrams are important because you will find the applications of question in network only with the help of these two diagrams. Okay, so once we will see this diagram and another will see this diagram. Okay, now further we try to understand few more concepts of op-amp. Okay, now the first very important thing, as I said, it is an operational amplifier. So op-amp is a class of amplifier, or you can say it is a class of high gain amplifier. First very important thing. Okay, operational amplifier op-amp is a class of very high gain amplifier. Please keep in mind. So if this is your op-amp, and if this is your op-amp, say this is voltage V1, this is V2, and this is output voltage V0. I said this current is I1, this current is I2. So the operational amplifier is referred as a very high gain amplifier. Now the meaning of high gain means, what is gain? Gain you always defined as the ratio of output to input. Yes, this is the definition of gain, or you generally refer gain as factor A, or you can call it as A V0 by Vi. So this is basically your gain. Okay, so in operational amplifier, the gain of this op-amp, if I call the gain, so for the timing, if I call this gain as A, so the gain of operational amplifier is very high, or ideally you can say it is infinite. It is infinite. Now I have used one word known as ideal. Okay, I have used one word known as ideal. One by one we will understand the concept. Please try to go through every word what I am explaining you here. Okay, so first of all, I explained that what is op-amp, what are the terminals, what is the meaning of powering of op-amp. Now in next point, I mention you that operational amplifier is an amplifier having a very high gain. So it is also known as high gain amplifier. And what is the meaning of gain? Gain, we know that it is the ratio of output to the input, or you can say it is A, that is denoted by V0 by Vi. So here if I consider this case A, so you can say that your output is some value of A into the difference of the voltage. So we will see what is that actually, but for the time being, as I said, the high gain, the amplifier is having high gain. That means ideally I can say this gain is infinite. Now the very important word which is coming here is known as ideal. What is the meaning of ideal? So that means the one very important thing which comes to your mind, that if some ideal things are existing, then practical things are also existing. Yes, so you can say that op-amp is basically divided into two classes. First one is known as ideal op-amp and another one is known as practical op-amp. Okay, this is known as practical op-amp. So in network we will more focus upon the ideal nature of an op-amp. Please keep in mind, while we are going through the problem solving sessions, we will more focus upon the idealistic nature of an op-amp rather than the practical nature. Okay, your practical op-amp problems you will find in your EDC subject, that is electronics and devices circuit, but for a network point of view, we will more focus on the idealistic nature of an op-amp. So as I said, op-amp is classified into two parts. One is ideal op-amp and another one is practical op-amp. Now we will see what do you understand by ideal operational amplifier and what is the meaning of a practical operational amplifier, or you can say non-ideal operational amplifier. Okay, that we will see. This is your I1, this is your current I2. Okay, voltage V1, V2 and V0. So as I said, ideal op-amp, the meaning of what do you mean by ideal op-amp? So the meaning of ideal op-amp, just try to understand that, as I said, the gain of an op-amp A is very high, or ideally you can say it is infinite. That means if I draw its equivalent circuit, okay, see, this is representing in some of notation, but you cannot solve this network until unless this operational amplifier until unless you can convert into its equivalent network. Okay, so if you see, the op-amp is in this form. Just try to understand. From there we will try to get the concept of op-amp. So friends, now please see this. What I did, I just convert this triangular figure in this way. Okay, now as I said, we are trying to get what is ideal op-amp. So this is its equivalent diagram. Okay, so here are the two terminal V1 and V2. Some voltage, that is known as differential voltage, produced here, we call it as VD, and at the output, this should be your output resistance R0, this should be your input resistance Ri, and whatever the difference is created here is converted into output in the form of AVD. We just now say that A is your gain, or you can say operational amplifier gain, but we will see what the meaning of A is actually. Okay, so if you see, the operational amplifier states that it has a specific property that the input resistance of operational amplifier is very high. Ideally you can say it is infinite in nature. So if the value of this resistance is infinite, please try to understand, the value of resistance of this network is infinite, you can say that whatever the current present here will be zero. Yes, will be zero. Okay, for the time being I have taken this direction. Please don't confuse with that direction. You said if this is the direction, then it will be in opposite direction, so that is a different matter. But for the time being I am taking, if this is an I1 and this is an I2, and if there is a very high resistance at this position, so you can say that if Ri is infinite, you can say that I1 goes 0, I2 goes 0. And if I1 and I2 goes 0, that means you can say that V1 and V2 are equal. You can say that V1 and V2 are equal. The meaning of Ri infinite, it means what? It means you can say that if Ri goes infinite, it means I goes 0. It means no current will flow from here. or it behaves like an open circuit. It behaves like an open circuit. Now, if you just try to understand it, in network we have seen that this condition is somewhat like this. Here is the voltage V1 and here is the voltage V2. So, as per the condition, if no current will flow here across this, so this voltage V1 and V2 get equal. When you apply a KVL, so V1 minus of V2 or V2 minus of V1 goes what? 0. Okay, just by applying a KVL loop here. So you can say that the value of V2 and V1 is equal. So this is basically known as the concept of virtual ground. This concept is basically known as the concept of virtual ground. Please keep in mind, this concept is known as concept of virtual ground. The meaning of virtual ground is see, we have seen two different type of condition we will discuss here and just try to understand. Okay, in this condition some current will flow from V1 to V2, but what is that current we don't know. But because of this, if you apply, if it is minus plus, this is also minus plus, so if you apply one KVL, you can say V1 minus of V2 is what? 0, or you can say V1 equal to V2. Now you see here it is connected by some branch, but still you find that the value of V1 and V2 is 0. That means here is no current, or you can say these two nodes are of common potential. Okay, the meaning of V1 is equal to V2, that the node is of common potential. But in networks we will see that it is connected by some branch. So here the current is 0, but you will find that these two nodes are connected. Okay, these two nodes are connected. But now if there is another condition, please try to understand. If this is another condition, I am just redrawing it. So this was our first condition, this was our second condition. Now please try to understand this condition. If you find the voltage at this point, okay, what is this voltage? Just by applying the voltage division, it is 4 into 2 upon 2 plus 2, that is 4, that comes to be how much? It is 2 volt. So here the voltage is what? 2 volt. Now if you find this, it is 16 into 2 upon 14 plus 2, that is 16. Again it is cancelled down, that comes to 2 volt. So here also what is the voltage? 2 volt. So now you see these both nodes are having same potential. Okay, both the nodes are having same potential, but it is not connected. That means here the ground is connected, but here that ground is not connected. So we will call a virtual ground condition is existing between these two nodes. Okay, why? Because the potential at both the nodes are same. Very important thing, the potential at both the nodes are same, but it is not connected. If you see physically, it is not connected. So we call it as a concept of virtual ground. Still the nodes are not connected, but virtually they are actually connected to the ground. That means the value of current is 0 and both the node potential are equal. So this concept is applicable in operational amplifier. Okay, and with the help of these two concepts we will solve the many problems. So just keep in mind, whenever there is an ideal operational amplifier, so the condition of ideal operational amplifier is that its input resistance is infinite, its gain A is infinite. So as I said, when we are talking about the ideal operational amplifier, so I said the gain is infinite nature, its input resistance is infinite nature. There is a very important condition that the two terminal voltages, okay, either it is an inverting or a non-inverting, or a non-inverting and an inverting. Okay, inverting, non-inverting, non-inverting, inverting. Okay, so whatever the voltage at both the terminal is always equal, and the current, that is I1 I2, is what? 0. This is a condition of ideal operational amplifier. Now there are few more conditions from here we will see. In case of ideal amplifier, as I said, A is infinite, Ri is infinite, the output resistance is almost 0 ohm for ideal condition. Right now we are talking only about the ideal condition of an amplifier. Okay, here output resistance is what? It is 0 ohm. So these are the few very important aspects of ideal operational amplifier. Okay, so this is all about the ideal amplifier. Now again we come to the term known as A. This A is known as open loop gain. Now I have changed its name, and now I term this gain A is known as open loop gain. Okay, this is known as what? Open loop gain. Now the very basic question comes to in your mind, what is open loop and what is closed loop? Okay, so first of all we will try to understand it. If this is an OPAMP, for the timing please consider it. Okay, and these are its terminal. Say this is its output terminal. Actually OPAMP is in the form of two input terminal and one is output terminal. So if the same OPAMP with output is now connected in this fashion, so when output is fed back to input, it is known as closed loop system, and when no output is fed back to input, it is known as open loop system. So this is your open loop system and this is your closed loop system. Okay, so this is your open loop system and that is your closed loop system. So now a question comes to in your mind, why we have talked about the open loop gain A. As I said, there is an A known as open loop gain. So definitely this open loop gain is the gain of this OPAMP when there is no loop. So as I said, the open loop gain of OPAMP is very high. Okay, the open loop gain of operational amplifier is very high, and when you go through your ADC subject, you will find that whenever the gain of an amplifier is very high, the output will become unstable. Okay, the output will become unstable in nature. Why? Because of this very high gain, the various other parameters or various other critical conditions created at the output, that is because of distortions, that is because of harmonics. So what will happen? The output will become unstable, and at that instant it is very difficult to measure the parameters at the output, and that's why a new concept introduced known as closed loop. What we will do, we will add some portion of this output to input. Okay, add, it means we will take from here and we will add and subtract it here. Okay, either we add it or we subtract it. Now the point comes to be either we add it or we subtract it. So there are two categories. You can say that it is a positive feedback, and if you subtract it, it is known as negative feedback. So there another term used to become known as feedback. So as I said, this is an open loop, this is closed loop. So closed loop means you have to connect output to input by some loop. Now the property of loop, or you can say it's a kind of feedback. It's a kind of feedback. Whatever is coming at the output, you have just taken it some part and bring it here. Now whatever the thing you bring it here, it is either in the form of addition or subtraction. So if it is addition, you call it as positive feedback, and if it is subtraction, you call it as negative feedback. Now you will see there are large application of negative feedback. Why? Because negative feedback, what it will do, it will try to stabilize your output. Okay, why? Because of very high gain, what will happen, this output is fed back and it is subtracted here, and again that is adjusted in the op-amp, and finally you will get an stable output. Okay, you will get a stable parameter at the output of that op-amp. So that's why you will find there are a large class of applications of negative feedback in an amplifier, and you generally call it as negative feedback amplifiers. Okay, now you will ask where the concept of positive feedback is used. So you will see the concept of positive feedback is specifically used in oscillators. Okay, you will study in your ADC subject. Oscillators, it means these are the electronic units in which the oscillations get increased depending upon the value of feedback applied. So positive, it means whatever the signal is coming here, it is again added into it and you will get an output. So oscillators are the units in which you will find a very high oscillations. Okay, so oscillators are basically using positive feedback, but when you are talking about an operational amplifier or any class of other amplifier, you generally use negative feedback, and negative feedback is specifically used to stabilize the output parameter. Okay, so we just seen that the ideal operational amplifier is of, we have categorized in two forms. It is either in the positive feedback or negative feedback. First, it is open loop in nature, another one is closed loop nature. Now what is closed loop? Closed loop is again divided into two parts, positive and negative. In our problem solving session, we will see how the positive and negative feedbacks work, but mainly we will focus on negative feedback concept. Why? Because in operational amplifier only negative feedback is used. As I said, it is a very high gain amplifier. Okay, now we will see the next thing. Now as I said, we are more focused upon negative feedback. So now first of all we will understand about this. For the timing, F I am just writing is as feedback. So what will happen, you will take V naught from here, okay, and you will subtract from your input so that get an stabilized output. Okay, so whenever it is added into a inverting terminal, it is basically a kind of negative feedback, but when it is added to a positive terminal, it's a kind of positive feedback. Okay, so now feedback, it is in the form of our basic three elements. One is your resistance, another one is your capacitor, another one is your inductor. Okay, so either resistor, either capacitor or inductor, and when these are added in the form of feedback, the amplifier performs different type of operation. It also performs summing operation, it acts like a differentiator, instrumentation amplifier, follower. There are a lot of applications of operational amplifier. You will find when you use C, it acts as an integrator as well as a differentiator in different manner. Similarly, when you use L also, it acts in a differentiator as well as an integration manner. But the very important thing, you will see generally L is not used. Okay, in electronics, in electronic devices and circuits, you will find there are a limited use of inductor L. You will see why it is. For the timing, I will explain you that inductor actually it is a bulky. It is a bulky element. When the frequency of operation increase, the element will become highly bulky in the nature, and that's why it is not much used. Okay, it is not much used in electronic circuits. You will only find the applications of R and C. But yes, in networks we will try to understand the numerical problems with the help of all these three elements. Okay, so this is all about the feedback, and in feedback what are the different type of combinations of elements are used. So these are the three elements. Okay, so now from this diagram I can say that V1 minus of Vd minus of V2, this is minus 2 plus V1, okay, this is plus of V2 minus of V2, that is equal to 0, or you can say V2 minus of V1 is equal to Vd, means that your difference voltage is what? V2 minus of V1. From here simply I have applied one Kvl equation. So This is your Kvl equation. Okay, so V1 minus 2 plus plus of Vd minus of V2 is equal to 0. How I should apply this? In this manner. Okay, this is negative, positive, again this is positive, negative. So minus 2 plus V1 minus 2 plus Vd plus 2 minus minus of V2, that is equal to 0. So you can say that your differential voltage Vd is what? V2 minus of V1. As I said, the value of Ri is very high and the value of R0 is almost 0. The value of R0 is almost 0 under ideal conditions, so it will become short circuited. So you can say that V0 is what? Is basically your A of Vd, or you can say that the value of A is what? That is V0 upon Vd, or you can say it is V0 upon V2 minus of V1. So this is basically your formula for open loop gain. As I said earlier, open loop gain is basically the ratio of output voltage to the ratio of the difference of input voltage, that is your Vd. Now how A is very high? We'll see the reason of A is very high because of this difference voltage. Okay, as I said, in ideal amplifier, in ideal operational amplifier, V2 minus V1 is what? It is 0. So once it is 0, the value of A goes infinite. Yes. So this is the condition of an ideal operational amplifier. However, in practical amplifier, you will find the value of V2 minus V1 is not 0, but it is very less. I mean, it is in the form of either micro value. Okay, it is in the form of micro value. I mean, it is in the form of microvolts. So difference of microvolts comes to be microvolt, but when you calculate it, it comes to be in the mega form. So that's why the amplifier gain in terms of operational amplifier is very high. Okay, and this is the reason. So that's why we taken A as infinite. So this is all about the ideal operational amplifier, and once again I will list the very important aspects of ideal operational amplifier. So as I mentioned here, this is an ideal OPAMP having 6 different type of parameters. So one by one we'll discuss what are those parameters. So first is A, that is known as voltage gain. Why I am calling it as voltage gain? It is because it is the ratio of output to the difference of input voltage. So this is basically your voltage gain, and that's why these operational amplifiers are also known as high voltage, high gain voltage amplifier. Okay, voltage amplifier. Please keep in mind, these operational amplifiers are also known as high gain voltage amplifier. Why? Because of their high gain, and that is basically a voltage gain, so it is also known as high gain voltage amplifiers. This Ri is known as input resistance. This Ri is known as input resistance, and in case of ideal OPAMP it is infinite. This R0 is known as output resistance. In case of ideal operational amplifier it is 0. BW is known as bandwidth. Bandwidth in a nutshell I will explain you, like it is a useful range of frequency under which the amplifier performs its operation. So it is not that of much use in this subject, I mean in network analysis, but just for the timing you remember the definition of the bandwidth. It is a useful range of frequency. So in your electronics devices circuits you will see what is bandwidth and how it is applicable. However, any problem which concerns to bandwidth in networks we will see. Okay, the Cmrr is known as common mode rejection ratio. Common mode rejection ratio, this we will see later. What is common mode rejection ratio? Sometimes a problem used to come, and this is known as slew rate. Okay, this is known as slew rate measured in volt microsecond. Just for the understanding, slew rate basically defines the property of an OPAMP, that how OPAMP responds effectively at output. That is defined by the parameter known as slew rate. So these are the 6 different parameters of an ideal operational amplifier, and you just keep remember these are the 6 parameters. Depending upon the usefulness of this parameter during our numerical problems, we will see what is all these parameters. Okay, so this is all about the ideal operational amplifier. Now we'll see the concepts of practical operational amplifier. So see, ideal amplifier are the one which we have seen the different type of condition, but actually ideal amplifiers is just a concept. In entire electronics you will find the applicability of a practical operational amplifier, and your practical operational amplifier always use with feedback. Always use with feedback. Some feedback is there. This is your V1 and this is V2. As I said, the open loop voltage gain A, which I called it as voltage gain, or you can say it is open loop voltage gain or open loop gain. Okay, different words are there. So voltage gain or open loop voltage gain, this is known as your A. So for an ideal op-amp, A is very high, that's why it cannot be used. So what we'll do, we will basically connect some output to input through a feedback, and we'll try to control the output parameter. Okay, and in this condition what will happen, it is required that the op-amp must be powered by some voltage. To control the operation of the amplifier by applying feedback, we have to power the op-amp with some voltage. This voltage is known as power supply voltage, and it is also denoted by VCC. For this it is plus VCC, for this it is minus VCC. So as I told you that the value of V0 is what? It is A V2 minus of V1. Okay, and when V2 minus V1 goes 0, when V2 minus V1 goes 0, your output goes 0. But this is not a condition, because V2 minus V1 is not a 0. It never remains a 0. It is a some value. So now the point comes to be, the condition is, you ask that if the value of A is very high, so whatever the voltage we will apply at the input of the operational amplifier, and whatever value we require depending upon the gain value A, will get that output. That means just try to understand this concept. If I said V0 is equal to A of Vd as per our equation first, so if say Vd is 1 volt and say A is 10 to power 3, so you will get V0 equal to 10 to power 3 volt. Yes, that means, just try to understand, you have applied 1 volt at the input of an op-amp, and with a gain of 10 to power 3 you will get an output of 10 to power 3, that is 1000 volt. Simply I am saying that by applying a very low value of Vd, that is 1 volt, with gain of 10 to power 3, you are getting V0 is equal to 10 to power 3 volt. Or you can say that if I apply Vd again equal to say 20 volt with A is 10 to power 3, I should get V0 is equal to 2 into 10 to power 4 volt. So that is a good condition. I mean, by applying a very low voltage, you will get a very high voltage at the output. Is it possible? Is it possible? This is only possible when we are talking about the ideal condition. But in practical, it is not possible. You will not get a V0. You will not get a V0 greater than the voltage which is powered for your operational amplifier. That means the value of output V0 is always restricted between these two values, that is your plus VCC and your minus VCC. So what I want to say, that the value of V0 will be lying between minus VCC to plus VCC. The value of V0 lying between minus VCC to plus VCC. This is the range of your output voltage V0 in case of operational amplifier which is non-ideal in nature. So this is never the condition. This is never the condition. Please keep in your mind. It's not like that you apply 1 volt with a gain of 10 to power 3, you will get 1000 volt at the output. This is not possible. The output of an op-amp is always restricted by the voltage which is used for powering the op-amp, or which is used to actually function the op-amp, and that voltage range is from minus VCC to plus VCC. Okay, so this is known as power supply voltage. So output of V0 is restricted between these two voltages. If I draw this graph now, please try to understand. This is a graph between VD and V0. V0 is what? Your output voltage. VD is your differential voltage. That is voltage, that the difference of the voltage applied at the input of an op-amp. So this is basically the characteristic of a practical op-amp, in which we will find that this is one region from here to here, in which you will find a linear property. You can call this as a linear region. This is known as linear region. Okay, and after that you will see this will be saturated. This will be saturated. Here also it is saturated. That means you can increase any value of VD from this value to a higher value. Similarly, from this value to a lower value. The output of an op-amp after this point will get saturated. Okay, the output of the op-amp after this point saturated. It means between these 2 points, between these two value, the nature of the operational amplifier is of linear region, but after that the op-amp will become saturated, and now it is restricted by the voltage through which it is powered, that is plus VCC to minus VCC. So in networks we will mainly focus on the operation of amplifier in a linear region. Okay, so in this topic, that is in op-amp, while we are going through the problem solving sessions, we will only focus on the linear region, how the operational amplifier work in linear region, and based on that we will solve the problems. So this is all about the practical concept, or the concept of a non-ideal operational amplifier. Okay, so this is one more important condition. From here we understand that yes, the value of V0 is restricted between minus VCC to plus VCC. Okay, so from here you understand that if you increase the any value of VD with respect to your open loop gain after a fixed value at differential voltage VD, the output of an op-amp will become saturated. The output of an op-amp will become saturated, and now it is independent of the condition how much VD you are applying, that is how much your differential voltage at the input, your op-amp will get saturated. So this region is known as linear region, and in this region only we will see the concept of networks problem. Okay, this is all about the practicality of operational amplifier. Now, as I mentioned the ideal nature of an amplifier, similarly we will see all the same parameter, that is A, then Ri, R0, then I mentioned as bandwidth, Cmrr and slew rate. So what is the condition in case? So this is all about the parameters of a practical operational amplifier. This A is again known as your voltage gain. Okay, it is also represented by AV. Just keep in mind. So it is AV. This is your Ri, input resistance of range of 1 mega ohm, R0 range of 10 to 100 ohm, bandwidth is around 1 megahertz. Okay, it's a kind of frequency, useful frequency. Cmrr is in the form of 10 to the power 6 or 120 dB, and this is your slew rate, which is around 80 to 100 volt per microsecond. Okay, now if you talk about one point which is known as CMRR. Little bit we will discuss about what is CMRR. Okay, we'll try to understand what is CMRR. Now you will ask what is common mode rejection ratio. So first of all, please try to understand CMRR. The formula for CMRR, it is given by AD upon AC. This is the formula for CMRR, where AD is known as differential voltage gain and AC is known as common voltage gain. Okay, so represented in form of CMRR in dB. So in dB it is basically 20 log 10, that is AD by AC. Just keep in your mind, this is formula of CMRR when we are talking about in dB. Okay, this is in dB. Now please see, if this is our OPAMP, this is condition 1, this is condition 2. Here the output of the OPAMP is the difference of the voltage, but here the output of the OPAMP is because of this common voltage which is applied at these two terminals known as V1. Now you see what happened for the timing, if I call it as Vi. So what happened, OPAMP has a specific property, then it always try to reject the common voltage which is applied at the two input terminal of an OPAMP. As we have seen that if V1 and V2 is applied and the difference of voltage V0 is what? It is A V1 minus V2. So if you see, if you just connect this, it means if you make it as short circuited and apply a voltage Vi at this input terminal, so operational amplifier is having a property that it always reject the common voltage applied at its input terminal. So you can say that the value of AC in case of OPAMP is what? It is 0. Why? Because it rejects the voltage which is commonly applied at its input terminal. So here voltage of AC is 0, and that's why if you talk about the ideal CMRR, it goes infinite. The value of CMRR goes infinite when the value of AC goes 0. Okay. So this is the property of an ideal operational amplifier where the value of CMRR is infinite. It is because the value of AC is 0. The value of AC is 0. But when you talk about the practical amplifier, AC is having a very low value. AC is having a very low value, and because of this very low value, and since it is in denominator, the entire value of CMRR goes high. So as I said, the operational amplifier is having a property of rejecting the voltage which is commonly applied at its input terminal.